All right, hello, and good afternoon to everybody. We are, what is the day today? It is Wednesday. We're in another Wednesday. Almost done with week 4, which is crazy. After tomorrow will officially be, tomorrow marks the official halfway point in the summer session. We'll be 4 weeks in with 4 weeks to go, and it's crazy. It's gone by in the blink of an eye, if you ask me. Hey there. Prathana. It is a good afternoon. I think it is a good afternoon. What are some things? So we've got 4th of July weekend coming up. Let's get it indeed. I've finished writing exam 2. So just like I did with exam 1, I'll be posting some like a post, Avocado Gang, much like I did with exam 1, where I highlight the percentage, each concept on the exam, the percentage, all the points. One thing that this exam will be is it'll be a little shorter time-wise. It'll be 80 minutes long. I don't remember off the top of my head the number of problems, but it'll be up in the post that comes later today. So I do expect that the time constraint on exam 1, the time constraint on exam 2 will be a little bit, it'll be a little more time pressure than exam 1. So that's something to start mentally prepping for, gearing up for, and even as we're about to all enjoy a 4th of July weekend. Shorter for longer problems. but Brianna, there will not be as many problems. There will not be as many problems, though. Some of the problems will take longer to do, but less time to cry. Exactly, that's another way of looking on the bright side, Peyton. Totally less time to cry. Because I think the last one was like an hour and 40, and this one's going to be an hour and 20, so there will be 20 minutes less for tears during the exam. Afterwards will be totally up to you. But again, this will not be this weekend, it'll be the next weekend, so this weekend is really time to start gearing up and preparing for that. The focus again is Chapter 5 and Chapter 6. Chapter 6 are where you're going to find a lot of the longer problems, mathematically heavy problems. And then Chapter 5 is, again, all about Lewis structures, geometries, polarity. And honestly, here's some advice, right? For the exam. And you can take this or leave this, but the advice that I would give is, if you know, i.e. memorize, your geometries, it will save a ton of time for you on the exam. All right, if you know your geometries and you can just spit them out, then you're going to be able to burn through those problems and spend more time on the stoichiometry calculations, which will take a little more. You know what I'm saying? So that's one way to save a ton of time, is if you really, really have those geometries down. There will be some problems where I give you a loose structure and you've got to spit out the geometry. There will be other problems where I give you the formula, so you'll have to draw the loose structure and then do the geometry. Again, I'll be posting a ton more of information. I'll be posting more information about the exam on Canvas, so you'll be able to feel that situation out, just like I did with exam 1, and hopefully it'll inform how you choose to study for exam 2 over the weekend. Again, we're still, it drops a week from Friday, so there's still time. There's still a weekend in between to study for it, and then, just like with exam 1, you'll have any time between Friday and Sunday. Anytime that weekend, you'll have to take it. So you can even study Friday, study Saturday, take it Sunday. Anyways, you guys know the drill. Before diving into lecture, there are 2 words that I'm writing on the board, and if you have never read or heard those 2 words before, I suggest checking out our daily mixtape, because if I had to be trapped on an island and could only listen to one artist's discography, this is the name that I pick hands down. If you're unaware of him, check him out. Tom Waits. He's weird, but he's a taste worth acquiring. So that'll spice up your Wednesday like nothing else will. All right. With that, let's go ahead and dive into chapter 7, a day ahead of schedule, which is actually cool. We're supposed to start chapter 7 tomorrow, but we're starting today. And it's nice when we can get ahead of the lecture schedule just a little bit, because it allows for more flexibility on the back half of the semester or summer session. All right, so totally. Okay, let's see. So, chapter 7 is about the states of matter. All right, the states, states. Sometimes these are called phases. Whoa, it's not mean for that to come out green. Of matter. It's interesting, actually. I mean, these things are the states / phases, different names for the same thing. When I was coming up as a spry young chemist back in the mid 2000s, like 15 years ago, these were called phases. I mean, they're called states too, but phases was the predominant word, and I've noticed our textbook uses states to refer to them. So they're the same thing, they refer to the same thing. I tend to say phases more than states, so if you listen to lecture and you're like, you're like, wait, I'm reading the book now and they're talking about states, but you're talking about phases, what's the difference? They're the same thing. And the 3 main states of matter, the ones that we'll be looking at in this chapter, are solids, liquids, and gases. Right? Solids abbreviated with a little s, liquids with a little l, gases with a little g. All right? Now, to begin this discussion of the states of matter, we're going to start by talking about something that's known as the kinetic theory of matter. All right, the kinetic theory of matter. All right, and really, if we're going to dig into this, we need to know what this word kinetic actually means. All right, kinetic is a word that means motion. All right, kinetic means motion, and I'm sure you've heard the word kinetic energy thrown out around there. When we talk about kinetic energy, we just got to lay down these kind of ground rules in order to kind of discuss and talk about what the kinetic theory of matter states. But so kinetic energy is energy associated with motion. All right, this is energy associated with motion. All right, so we could say that a Porsche doing 120 miles an hour on the freeway has a lot more kinetic energy than my Prius that's barely chugging along at 60, right? The more motion, the faster the motion that any particular object has, the more kinetic energy they have. It's energy in motion, all right? Sonic the Hedgehog, kinetic energy, right? Kinetic energy is contrasted with potential energy. All right, potential energy is energy whoa, where's my eraser? There we go. Potential energy is energy associated with position or composition. All right? Energy that is associated with position or composition. What do we mean by this? Well, when we talk about energy that's associated with position, what we're talking about is like if you roll a rock up a hill, all right, and it's, where's my camera? Sitting at the top of the hill, right? And you push it and it falls down. At the top of the hill, it had potential energy, which can be converted when you shove it down the hill and it starts rolling into kinetic energy, all right? Potential energy can be changed into kinetic energy, and at the top of the hill, there's a lot of potential energy. At the bottom of the hill, there's not a lot of potential energy. Or we can talk about potential energy can be associated with composition. So, for example, gasoline has a lot of potential energy in its bonds, and that energy becomes released when we burn it, and all that heat is released. That heat doesn't come from nowhere. It was the potential energy stored in the composition of gasoline that gets released through a chemical reaction, all right? So the best way to think about potential energy is energy that is stored. All right, potential energy is energy that is stored. And the way to think about kinetic energy is kinetic energy is kinetic energy is energy there we go energy that is being used. Is another way to think of kinetic energy, as opposed to potential. All right, and we're going to need both when it comes to talking about the kinetic theory of matter. Okay, Susan, question. So potential energy in terms of position is directly related to... Yes, exactly. Okay, so like position could be related to gravity, could be related to magnetic field. Okay, and then as far as composite, so Susan's question is, with position, potential energy is directly related to gravity. So with composition, what would you say potential energy is related to? Susan, that gets to the heart of the matter that chemists are most interested in answering. So when it comes to composition, potential energy is directly related I promise I can spell, to the bonds in a compound. Chemical bonds store potential energy, and breaking them releases it. So potential energy in terms of composition is stored in the chemical bonds, all right? They're holding that energy. They're like energy canisters. And when we break those bonds through reactions, we release that energy into the surroundings, all right? And that is why burning stuff, why things get hot, because we are releasing the energy that used to be stored in the fuel. Fuel is simply a word for anything that is a good source of potential energy, that stores a lot of potential energy in its bonds that can be released otherwise. Susan, that was an excellent question. Excellent question. All right, so we've got these two flavors of energy, kinetic and potential. Now, when it comes to the kinetic theory of matter, there are a lot of like technical definitions that I'm really not interested in getting into. I would rather give you kind of the big picture concepts behind behind the kinetic theory of matter. And these are kind of like the takeaways that I want you to have moving forward. First, and again, we'll use this throughout the course. We'll talk about these concepts as we talk about different phases of matter. But the central idea to the kinetic theory of matter is this. It's all matter is in constant motion. And when I say constant motion, I'm even talking about solids. All right, all energy is in constant motion, even solids, and the amount of motion, which is, right, we know motion is kinetic energy. The amount of motion is determined by the phase. Yes, Prathana. Great question. Does ice have potential energy? It does. any structure with bonds has some potential energy that can be released under the right circumstances. Great question. All right, so all matters in constant motion, even solids. Now, that you might be going like, really? You know, and you'll look down at the table that you're sitting at, right? Or the computer screen that you're looking at, and you may be going like, it doesn't look like it's in motion to me. Like my table doesn't look like it's moving. Well, on a macro scale, we can't see it directly, we don't observe it, but on a micro scale, the atoms that are composed of the solid state are like rammed into each other, right? But they're vibrating back and forth. They're like buzzing. They can't go anywhere because they're in the solid state, but they're still just kind of like moving around a little bit, right? There's not a lot of motion, not a lot of kinetic energy associated with the solid state, but it's still there. It's still happening. All right, Susan, is this how scientists are measuring the location and pullback of black holes? If I'm being totally honest, Susan, that is an excellent question. If I'm being honest, I don't actually know. That is more of an physics question, which is a bit outside my field. All right, so all matter is in constant motion. The amount of motion is determined by the phase, and the amount of kinetic energy associated with each phase is as follows. The kinetic energy of the gas phase is greater than the kinetic energy of the liquid phase, which is greater than the kinetic energy of the solid phase, right? So in the solid phase, we have the smallest amount of motion, right? Just a little bit of vibrations in the liquid phase. Things are a little more like flowy. With the gas phase, they're all bouncing all over the place, right? Lots of motion in the gas phase, some motion in the liquid phase, almost none, very little, but still there, motion in the solid phase. All right? So that's the first thing. Now, the second big thing when it comes to the kinetic theory of matter, and this is something that we've actually kind of laid the groundwork for in chapter 5, actually, and we'll come back to it in this chapter, talk a lot more about it. But all matter experiences attraction and or repulsion. Oops. And or repulsion with other matter. And this, either attraction or repulsion, creates potential energy. This means that the position of matter gives it some amount of potential energy. All right, some amount of potential energy. And again, this is because if all matter experiences either attraction or repulsion, if you have two pieces of matter that repel each other, if you move them closer, they've got potential energy that want to fly apart, turn that potential into kinetic. If you've got two things that are attracted to each other, they're pulling into each other, and so the further away from they are from each other, the more potential, and then the closer it converts to kinetic as they move together to collide. So the attraction and or repulsion that matter has for other chunks of matter gives all matter some degree of potential energy. All right. Third, and again, this is kind of like a conceptual tour, and we will be using these concepts to explain phenomenon as we move through this chapter and beyond. But third, the velocity, and if velocity is not a term you are familiar with, for our purposes here, you can think speed. Any people who are physics adepts in the audience will, that sounds like fingernails on a chalkboard. Don't worry, I know the difference between velocity and speed, but because it's not a physics class, you can consider these the same thing for now. The velocity of matter determines its kinetic energy, right? And that makes sense. The faster something is, the more kinetic energy it has. The slower something is, the less kinetic energy it has. And dovetailing on that last thought, velocity increases with temperature. All right, so the faster something's moving, the higher temperature that sample of matter will have. All right, the higher temperature it gases, the faster those gas molecules are moving. Even with a solid, you're like, but solids aren't moving very fast. Right, but a hot solid, these things will be vibrating back and forth very fast, as opposed to at a low temperature, the vibrations slow down. So even though it's bonking back and forth, the speed at which they're bonking back and forth is determined by temperature, all right? And that speed could be very fast, or it could be very slow, depending on the temperature. All right, fifth. And finally, and this is a very important concept for the kinetic theory of matter. I'd say of all the ones we talked about, the first and the fifth are the two most important ones, right? So this one is energy is transferred through collisions. All right, energy is transferred through collisions with other matter. All right, as matter comes into contact with other matter, energy is transferred through that contact, through collisions. It was funny. I was writing out my lecture notes the other day, and the morning that I wrote this lecture, so my wife's a nurse, and so she has to leave crack of dawn. I make her coffee, get her out the door, and then I've got a few hours before the kids start waking up where I can get classwork done. And so I wrote out the lecture notes, and kids start waking up and we're hanging out, and my daughter gets a bowl out of the dishwasher, and the bowl is hot, right? So the temperature of the bowl was very, very hot coming out of the dishwasher. I'm actually going to draw it like this because it was hot. And she took milk, poured milk in the bowl. Look at my super awesome graphics. And all of a sudden she goes, "Whoa." I was like, "What? What's up?" And she was like, "My bowl is really warm, but now half of it's warm, half of it's not." And I was like, "What do you mean?" She's like, "Well, the bottom part where the milk is cold, but the top, the rim of the milk, is still warm, still hot." And I was like, "Oh, it's funny is I was writing about this in lecture for my lecture notes. It's because the milk has come into contact with the bowl and the milk came out of the fridge, so it's cold. And through the collisions of the milk particles with the side of the bowl, that lower part got cooled." All right? And she was like, "Huh." And then she felt it and she's like, "Oh, but now the top isn't hot. The top is kind of cooled down. It's not as cold as the bottom, but it's kind of warm. Why is that?" And I said, "Well, as we've been talking, the hot top of the bowl has been in contact with the air. And those collisions with the air in the atmosphere has the top part of the bowl, that lip, that rim, has exchanged energy with the air through collisions, and so now it's the same temperature as the air around it." And it was super cool because I literally had just written this lecture about energy being transferred through collisions of matter with each other, and then she empirically experienced that happening as she got a hot bowl out of the dishwasher, poured some milk into it, and then eventually the whole thing cools down to room temperature. So that's kind of like a working knowledge. Again, you're going to read things. If you read the book, it'll start talking about elastic collisions, all that stuff. You don't have to worry about the technical side. I really want to want us to focus on the conceptual side of things, the big concepts. This is how matter works. This is how matter moves. This is how matter interacts with other matter. All right? Yeah, it was totally awesome. It was a beautiful serendipity, and it was also science in a bowl of cereal. All right, so well, thank you, Brianna. We'll that is very, very kind of you to say. Hopefully, I'll be helpful eventually. Sometimes it's hard learning from your parents because you don't want to. I haven't experienced this with my kids. I did experience it with my little brother, though. I was a chemistry major. I was away in college, and he was taking chemistry in high school. And I was home one weekend, and my mom was like, "Oh, you should help him out." So I was like, "Oh, okay." And we were talking, and I was like trying to explain the thing to him. And he's like, "That doesn't make sense. I don't get it. I don't get it." And we ended up getting into this huge fight. He told me years later, we're older adults now. I was a baby adult then. He was in high school. He told me later that he was like, no, I remember that day. It totally made sense. I just didn't want to learn from you, so I pretended it didn't. And then when Mom explained it to me, he was like, yeah, I got it. So anyways, we'll see what happens. I'll be available to my kids for learning, and they can take advantage of that or not. That is their call. So with the last thing, we're kind of going to do one last big picture thing about all the phases, and then we're going to look at individual phases. We'll take them one at a time, starting with the gas phase. But so some they got a lot of lulls. But no rolling on the floor laughing, which could totally happen, and we wouldn't know or see. That's one, I guess, advantage of an online class is you can decide to roll on the floor while laughing, and it doesn't disrupt the rest of the class. Okay, so big picture, talking about when we talk about solids, liquids, and gases. And these are all things that'll be relatively intuitive, but I think it'll be helpful to kind of line everything up to compare them. So we can talk about the volume and the shape of each. Okay, now someone's rolling on the floor. That makes me happy. We can talk about the density of each phase. We can talk about something called compressibility, or how compressible is something, and then we can talk about thermal expansion. When you heat something, how much does it expand? All right, and for solids, all right, solids have a definite volume and they have a definite shape. All right, the volume doesn't change, the shape. The shape doesn't change. Like my mug, it has a volume and it has a shape, and those things aren't going to change, right? The solid phase is very, very rigid. Solid phase, matter's packed in very tight together, so it tends to have a very high density. All right? Solids, in general, have low compressibility. And when a solid heats up, will it expand? To some degree, yes. But in general, solids have a experience very low thermal expansion. All right? So solids tend to be the most rigid, the most dense. They don't change a lot. And they're contrasted with gases, which are extreme, right? The volume of a gas is indefinite. Right? A gas will fill any space you put it in. The shape of a gas is indefinite. Again, it'll fill any space that you put it in. So gas is very amorphous, very loosey-goosey. This is the difference between earthbenders, which would be solids, and airbenders, which would be gases, right? Very flowy, very non-committal, where earthbenders are like solid, rigid. If you haven't ever watched Avatar: The Last Airbender, as of like 2 weeks ago, you have no excuse because it's on Netflix. So binge watch it this weekend if you haven't seen it already, or if it's been years. It was actually last year. My wife and I sat down to watch it with our kids, and it was awesome. Experiencing them experience it. So, yes, totally. And one thing that I actually like about it is there's a lot of really good analogies with science. Like, you think about earthbending, and earthbenders as solids, airbenders as gases, right? And it's purposeful. They actually conceptually sculpted them based on the different... Exactly. Toph is a solid, Aang is a liquid, and guess what Katara is? She's the flexible middle between. Yeah, totally. Okay, so let's finish our gases here. Gases, are they dense? Not at all. They have very low density, all right? But their compressibility is large. Peyton, you've got a good boyfriend. If he's like, we've got to watch this together. That's how you know you got to keep it right there. Yes. I actually haven't thought about Momo for a while. Brianna, thanks for throwing that up in the feed. Oh my gosh, that's amazing. Esther, that is so stinking cool. My kids would flip out. I would flip out as well. Yes, totally. So gases low density, they're not very dense, but they have a large compressibility. You could take all the gas that's in this room, filling up this room right now, and compress it down into the size of this coffee cup. All right, it'd have a high pressure, but it can still be compressible. Heck yeah. Dude, oh yeah, I mean, who doesn't love a caterpillar bison that flies? It's like every kid's dream. Alright, so large compressibility, and we would say that gases have a moderate thermal expansion. Experience a... yep. I just have to throw this into the feed. Okay. So, we've covered our earthbenders with solids, we've covered our airbenders with gases. Let's talk about our waterbenders with liquids. Alright? Liquids are the middle ground between your solids and your gases, right? Liquids have a definite volume with an indefinite shape. Right? They have some in common with the earthbenders, right? They're definite volume, they have a high density. They actually have a low compressibility, a lot in common with solids, but they have an indefinite shape, right? They're flowy, like air. I do have Zuko's original haircut right now. I totally do. I actually was and then low key doing the Sokka thing as well. So liquids, similar density to solids, similar compressibility to solids, but they have a similar shape to liquids, right? Indefinite shape, and more in common in thermal expansion. With the gases. And if you're wondering, okay, well, if solids are earthbenders, liquids are waterbenders, and gases are airbenders, where do the firebenders come in? They would be kinetic energy benders, right? Fire is kinetic energy; it's energy in motion. So, so that is where I guess fire would fit into the physical world that we inhabit. Whoa. Okay. Karenza, thank you for letting me know that you don't know how it ends. This must remain a spoiler-free zone. It totally will. But I'm so excited for you to experience it. It's good. It's not like one of those shows that it's like, oh, it was great until it ended, then it ended lame. It's satisfying all the way through. Susan, all you need to know is it is excellent. Family-friendly TV. It's entertaining for kids, but with compelling character development that will hook you as an adult. It's superb all the way around, and it's on Netflix. So if you got Netflix, you can do it. Okay, so we've set up the phases. We've talked about all sorts of elemental bending, but like Avatar: The Last Airbender is about an airbender, this chapter will largely be about one phase as opposed to the rest, and that phase is Aang's phase, or Aang's phase. Aang? Aang? I never know how to pronounce it. It's Aang. I know it's Aang in the show, but then when I see it on the written, I always go Aang. Okay. Alright, so, just like Avatar: The Last Airbender talks about all bending, but focuses on Aang, we are going to focus the majority of Chapter 7 on the gas phase, alright? Now, when you talk about different quantities with which we can measure matter, alright, we can talk about, volume, which is measured in liters. We can talk about the volume of, here, hang on. Let's see. All right. So, sorry, I'm just typing a response. If you're in a situation where we're not able to get in on the wait list to my Chem 400 class in the fall, but you want to, I can't guarantee you a spot, but what I can say is shoot me an email at the beginning of the semester, because what I'm going to be doing in the fall is the same thing I did for this class, where I send out everybody a copy of the syllabus. Everybody who's enrolled has to download it, fill out the syllabus quiz, and then return it. And everyone who doesn't, I drop. And then everyone on the wait list, I email them. And if you're not on the wait list, you can still try to crash the class. Send me an email. I'll email you the quiz. You fill it out. You send it back to me. You guys all made it in here, so you know the drill. Everybody who's enrolled in the class is dropped. Who does not fill out the quiz, and then the people on the wait list and the people who are crashing who do fill out the syllabus quiz and get it back to me are given priority. So again, I can't guarantee a spot, but there's still a chance, right, for you to get in, because most people don't respond, especially on the wait list. Most people don't email it back. I had a wait list of 20 people, and like 60% of them didn't respond. So there's still a chance for you to get in, even if you're not enrolled. And again, I can't promise, because it depends upon, there's a class cap, the maximum students I can enroll, and I don't know how many people on the wait list will respond, but let's keep our fingers crossed, and there's definitely a chance. So if you're not on the wait list and hoping to get in, or not on the wait list and wish you could, we can still try to work that out. Send me an email as at the beginning of next semester. We'll start it early, and hope for the best. Okay. All right. With that being said, let's talk about. So we know there are these physical quantities that can be measured, that we can talk about regardless of the phase. We can talk about the volume of a gas, liquid, or solid. We could talk about how many moles are present, and moles are symbolized with an N because M was taken for mass. And we can talk about the temperature of a solid, liquid, or gas. Temperature, often measured in Kelvin, though it can also be measured in, obviously, degrees Celsius, degrees Fahrenheit. But the one quantity that is really unique to the gas phase is pressure. Excuse me. You don't really, in normal circumstances and contexts, you don't really discuss pressure in terms with respect to any other phase other than the gas phase. I'm not saying you never do, right? My brother is a geologist, and the pressure of the outer layers and the mantles of the earth cause certain layers underneath to liquefy because the pressure of those solids are so great, right? So there's a solid exerting a pressure. Anyone who's ever seen a movie about, like a submarine movie, like Crimson Tide or Hunt for Red October, there's always that one part in every submarine movie where we're losing power, we're sinking to hull crush depth, right? That's that point in the ocean where the pressure of the water above the submarine will actually crunch the hull like a can, right? It'll compress in on itself, everybody dies. And don't worry, the engine always turns on right as they flirt with hull crush depth, and then they're fine. So, if you've never seen a submarine movie, I've just spoiled the tensest part of every one for you. Alright, so liquids, that's liquids exerting pressure. Scuba divers deal with liquid pressure, right? You can't fly on a plane because you'll get the bends because the difference in pressure. If you go too rapidly from being deep under the ocean to up top to flying, does bad things to your body, but it does great things for a Radiohead album. Their second album was named The Bends. If you don't know, now you do. So, it's not that solids or liquids can't or don't exert pressure. They just only do so under very abnormal extreme circumstances. The only phase that deals with pressure on a regular basis is the gas phase. And what we're going to do at this moment in time is we're going to look at how the volume of a sample of gas, the moles in a sample of gas, and the temperature of a sample of gas relates to the pressure of said gas. Okay, Parthana, I'm going to have to check that out. Because I love submarine movies. Alright, so we're going to look at how the pressure of a gas relates to these three quantities. I want to say a couple things before we dig into it. First is the order in which I address these is going to be different than what you see in the book. And for example, the book doesn't actually talk about how the moles of a sample of gas relates to pressure. But I'm going to. You'll be better prepared to handle this stuff when you hit Chem 400 if you do. But also it just makes sense because these are all the quantities that we talk about for solids and liquids. So we should talk about moles with respect to gases. Alright, now, so we're going to talk about how pressure relates to all of them. One quick caveat before we dive in is pressure units. Alright, there are many pressure units out there, and a handful that will be good to be familiar with. The metric unit for pressure is called the atmosphere. Alright, and atmosphere is abbreviated ATM. Now, an atmosphere of pressure is the pressure exerted by the atmosphere at sea level. So we're all more or less under about 1 atmosphere of pressure. All right. Now there's a ton of different pressure units. For example, you have the pressure unit called torr, Torr. 1 atmosphere is 760 torr. Another unit is millimeters of mercury. Usually barometric pressure was measured in millimeters of mercury. 1 millimeter of mercury is actually equal to 1 torr, so these two units are the same, they're interchangeable. English unit for pressure is PSI, pounds per square inch, and 1 atmosphere is 14.7 pounds per square inch PSI. Something to note is these unit conversions are exact. All right, so these will never limit your sig figs. This guy right here, though, because it's going from metric to English, it's not exact. This is a measured unit conversion, so this will limit you to 3 sig figs should you use it. All right. So with that, this is how we measure pressure in units of atmospheres, torrs, millimeters of mercury, PSI. There's even other ones. There's pascals, there's kilopascals, all sorts of pressure units. But the ones that I wrote on the board are the main ones that you'll interact with in this class. All right, now let's talk about pressure. And here's kind of a way to think about the pressure exerted by a gas. All right, if you ask a physicist, what is pressure? They would tell you that pressure is equal to a force applied over an area. All right, pressure is a force applied over an area. And if you're wondering, well, how does a gas exert a force? Gases exert forces. Susan, good question. I don't know if torr is short for something. Let's see what the internet has to say. The unit was named after a dude named Evangelista Torricelli, and his facial hair looked like a battle axe on his face. Look up his Wikipedia page. Here. I didn't know this until I Googled it just now. But seriously, look up his facial hair. On that link, it looks like a battle axe underneath his nose. And then with the where you grab the battle axe is underneath his nose, and where you grab it is on his chin. Really weird stuff. You learn something new every day. I just did. If I could, if I could grow that mustache, I could, but I can't. So I won't. Actually, even if I could, I don't think my wife would like it. So, how does a gas exert a force? All right, the way that a gas exerts a force on everything it comes into contact with, is through collisions. All right, it exerts a force through collision. So think about it. The air in this room that's surrounding me right now is constantly popping back and forth, hitting my body. All right, it's like a billion little tiny bullets of gas are hitting my body and bouncing off. That is the atmospheric pressure that I experience. Those collisions exert a force on my body, and that is the pressure that a gas exerts. All right, so what I'm about to do is going to differ. Oh my gosh. Brianna, you win. You win everything today. That is the best emoticon I've ever seen. At least with respect to physics. That is so dope. Alright. So, I'm about to present things in a little bit of a different fashion than the book does. But I feel like it makes more intuitive sense. So let's talk about how the pressure of a gas relates to the volume of said gas. All right, let's talk about a pressure and a volume. Now, I want you to consider two samples of a gas. We've got sample A in this nice big box. Let's say we got 3 moles of gas bouncing around in here. And then we have sample B. Same amount of gas, still 3 moles, but it's being held in a much smaller box. All right, which one would you expect to experience more collisions with, sample A or sample B? All right, think about that. Well, basically, I mean, you look at it and you go, well, it's the same amount of gas in each box, but because B is smaller, they're going to be hitting each other more, right? They're going to be hitting the walls more, they're going to be hitting each other more. And so we would say that sample B has more collisions than sample A, which means, yeah, Kate, exactly. Sample B has more collisions, which means that sample B will have a higher pressure. All right? More collisions equals higher pressure. Now think about that. Sample B has a smaller volume, but a higher pressure. That means that the pressure of a gas is proportional to, inversely proportional to its volume. Dude, yes! We all got to be watching some submarine movies this weekend. All right, the pressure of a gas is inversely proportional to this thing, by the way. This is a symbol borrowed from symbolic logic. This is an alpha. It's the A letter from the Greek alphabet. It means proportional to. All right, it means proportional to. And the reason is, if volume decreases, pressure is going to increase, right? As we saw with B, smaller volume, larger pressure. If volume increases, like A, pressure decreases. So these two quantities are inversely proportional. Susan, we'll talk about temperature in a little bit, actually, tomorrow. Okay, so alpha means proportional to, but it doesn't quite mean equals, all right? And the reason why we can't write pressure is equal to 1 over volume is because we have a unit problem. Pressure is measured in atmospheres, whereas volume is measured in liters, right? So we have atmospheres is not the same thing as 1 over liters. If we want to write an equals sign, we need to multiply this by a constant number. All right, this constant number will have units that will make these two quantities equal. This constant will have units of atmosphere times liters because it allows liters to cancel, and now you have pressure on both sides of this equation. All right, so this equation pressure is equal to, actually I want to keep this in, pressure is equal to a constant number, C, times 1 over V. Now we can use algebra to solve for this constant, right? If we multiply both sides by volume, volume cancels, and we get a new equation. We get an equation that says pressure times volume is equal to a constant number, which we've designated as C. All right, now think about what this means. Think about what this means. Let's say you have a pressure, some pressure of a gas, we'll call it P1, and you have a volume of a gas, and you multiply these two together, P1 times, V1. Well, if you multiply the pressure of a gas times its volume, what's it going to equal? That constant number C, whatever that number is. Let's say the pressure changes. Let's say it's a different pressure now. It's P2, the volume will change with it. Now it's a different volume, and you multiply those together. What do they equal? They equal a constant number, C. Because they both equal the same number, we now have an expression where your initial pressure multiplied by your initial volume is equal to the final pressure times the final volume. And get this, we do not need to know what that constant number is to be able to use this equation to solve problems. All right, to solve word problems like the following. So consider the following example. All right, a sample of gas has a pressure of 1.3 atmospheres. 1.3 atmospheres, while its volume is 2.5 liters. All right? If its volume expands to 4.0 liters, what will its pressure change to? All right. So a sample of gas has a pressure of 1.3 atmospheres, while it's at a volume, its volume is 2.5 liters. If its volume expands to 4.0 liters, what will its pressure change to? And the answer to this question we will do tomorrow in lecture. So try this. Try this at home. See if you can solve it, and we'll come back tomorrow and you can check your answer with mine to see if it's correct. All right, so we're going to put a pause today. Tomorrow we'll come back, we'll do this example, and then we'll continue exploring how the pressure of a gas is related to its other quantities, like the temperature of the gas, like the moles present in the sample, and we'll have a good time as we study the science of air bending. Thank you all to everybody who came out. Thank you to everybody who's watching later at your own time. I'll see you all tomorrow in class, and then office hours, and then we are halfway done with the summer session. Later, dudes.